All right, everyone, we're back. So now we can start to apply these solid mechanics or these linear algebra concepts to an example. So we can actually apply these towards solid mechanics concepts. So hopefully everyone remembers stress, strain. Stress is force per unit area, cross-sectional area, Newton per meter squared, Pascal. Strain, initial length or final length minus initial length over the initial length, unitless. And we have equations that we can relate stress and strain. So in the linear elastic regime. And so first we're going to be looking at basically materials that are linear elastic cubic isotropic materials. So stress is a second rank tensor property. And that tensor is symmetric, meaning if we take the transpose of this matrix or this tensor, it will be identical. And that has to do with basically applying your equilibrium conditions or your static equilibrium conditions, meaning that the sum of the forces, the sum of the moments must be equal to 0. So stress is a second rank tensor property. These are directions. So I indicates the normal to the cross-sectional area on which the stress is being applied. J is the direction of that force. So this is the tensor that we're working with. And so now we can start to write relationships between stress and strain in terms of our elastic constants, E and nu, which is our, basically, E is going to be our stiffness. It's our Young's moduli. And then you should know those from other classes. Nu is going to be our Poisson's ratio. And again, we could write a general way for linear elastic cubic isotropic materials to relate stress and strain in 3 dimensions. So we have this effectively this equation here. Epsilon ij equals 1 over my Young's modulus, 1 plus nu, sigma ij minus nu sigma kk delta ij. So delta is this Kronecker delta. And Kronecker delta will be 1 when I is equal to j and 0 when I is not equal to j. So if I want to write out the strain of the 1, 1, I'm going to write 1 over E plus 1 plus nu sigma ij, which is sigma 1, 1. And then minus, I'm going to go over all of the different indices that are kk or 1, 1, 2, 2, 3, 3. So minus 1, 1, 2, 2, 3, 3. And here's my equation for E1, 1. For when I is not equal to j, for example, for strain 1 and 2, it's just going to be this plus this here. This is 0 because I does not equal to j. Kronecker delta is 0 when I does not equal to j. So I could go ahead and write out those relationships here. But I want to clear this up. But it's pretty laborious to have to do this, and especially when you're trying to solve as well. So I could write out a series of expressions like this, epsilon 1, 1, in this kind of what we call a Voigt notation. So I could write out just a linear algebra concept. So this would be, you could call this your x or your b. Here would be my stress, and then this would be essentially, in our old notation, if we're looking at a dot x, let me comment this out. In our old equation, a dot x equals b. So in this expression, my s dot my stress equals epsilon. So I could rewrite this expression, this equation here, as a linear algebra expression. So I could look at this S matrix here, and I could do S dot stress, and I'm recreating my equation here. And I could also write it like this and solve for all my strain values. Exactly. So we recover, this is the exact same equation we wrote above here. So we can kind of do that. You'll notice that if we do, actually here it really doesn't matter the order in which we do that. We can also use this equation and solve for my stresses as well. And you can see that the relationships are the same here. So I could do inverse S dot epsilon, and I could recover again these relationships. So this is the key kind of concept here. So we could rewrite those expressions as linear algebra relationships. So very, very, very useful. Actually, we can kind of help ourselves out. Let's do this. Full simplify. And you can see. Let's do full simplify. And we can see the same relationships here. E2, 3, here, and we're good to go. So this is the nice kind of part of this expression. Remember, epsilon dot inverse S. Remember, order matters. So let's do simplify. So we want to keep our values. Actually, it doesn't well because we're symmetric here. So we can kind of look at and visualize this similarly. Excellent. So next time we are going to get into materials that are not linear elastic isotropic. So much more complex. We're going to look at a fourth rank tensor property, our compliance, and our stiffness tensors. See you next time. Thanks. Bye.